In the following problem, we're given a circuit with two real batteries, meaning they have internal resistance, and we're going to try to find the total current that's flowing through our circuit, as well as the power dissipated through some of the circuit elements. First, let's look at the three parallel resistors between points A and B. In order to combine these three resistors, we use our formula for adding parallel resistors. Doing so, we find that an equivalent resistor that could replace these three that are in parallel is 3 ohms. So what I'll do is I'll erase those three parallel resistors and simply replace them with the equivalent 3 ohm resistor. Now, let's take a quick look at the two real batteries. EMF1 has a 22 volt positive terminal on its right side, and EMF2 has a 7 volt positive terminal on its left side. For now, let's assume that the 22 volt EMF wins out when they push against each other and that the current flows clockwise through our circuit. In order to determine the total current that flows through this circuit, we need to find an equivalent resistor so that we can use V equals IR. Notice now that all of our resistors are in series. Even though the 2 ohm and 1 ohm resistors are internal to the batteries, we can still add our resistors in series. Doing so, we find that an overall equivalent resistor is 10 ohms. Now, as discussed earlier, having a net 15 volt EMF pushing towards the right, we now have V equals IR where we can solve for I. Doing so, we find that I equals 1.5 amps. Now, I'd like to make myself clear for a second here. When I say that the EMF pushes to the right or pushes to the left, I don't actually mean a force. The term EMF, or electromotive force, is a bit of a misnomer. There is in fact no forces here. There are no pushes or pulls. However, thinking about it this way at times can prove to be very helpful, and so I can't help myself but say push. If using this specific vocabulary makes you uncomfortable when it comes to voltage, you can also think about solving this problem using Kirchhoff's law. Think about starting in the top left corner of our circuit and making a full loop. We know that the current, I, will be running through each and every element in this equivalent circuit, and so we can sum all the voltage drops and gains as we go once around the circuit loop to give a net result of 0 as Kirchhoff tells us. Doing so, we will also solve for I equals 1.5 amperes. Okay, great. So now we know the total current flowing through our circuit. Part 3 of the question asks for the rate at which electrical energy is delivered by the battery 1 to the rest of the circuit. The rate at which energy is delivered can otherwise be thought of as power. We have a formula for power, P equals V times I. However, here we have to be careful. When looking at battery 1, we have to talk about the terminal voltage. What happens is that battery 1 tries to deliver an EMF of 22 volts. However, due to its internal resistance of 2 ohms, it can't give us that full 22 volts. It's incapable of doing so. Because of this, it delivers what we call a terminal voltage, a non-ideal value that you would measure if you put a voltmeter across the terminals of the battery. The terminal voltage is equivalent to the EMF it tried to supply minus the internal voltage drop inside the battery, the current that flows through the battery times the internal resistance. Multiplying this terminal voltage term times the total current through the battery gives us a power delivered of 28.5 watts. Now we want to know the power dissipated through the 9 ohm resistor from the original circuit diagram. We now know that the total current flowing through the circuit to be 1.5 amperes. However, when that current gets to point B, it will split up into 3 separate currents, one that goes through the 6 ohm resistor, one that goes through the 18 ohm resistor, and one that goes through the 9 ohm resistor. If we tried to do P equals VI to determine the power dissipated through the 9 ohm resistor here, we would have to solve for the current that goes through the 9 ohm resistor. This isn't too difficult, but there's an easier way. We also know that P equals V squared over R. We already have R being 9 ohms, and we know that parallel resistors will all drop the same voltage. Combining them back into the equivalent 3 ohm resistor, we find that the drop across the equivalent resistor to be 1.5 times 3 equals 4.5 volts. This is the potential that each of the three parallel resistors will drop. Therefore, the power dissipated, V squared over R, in the 9 ohm resistor will be 2.25 watts. As always, a link to the PDF version of the full solution is available in the video description below. Thanks for watching!